We have now reached the point in the semester where we'll learn how to solve trigonometric equations. In order to do that, we have to be very familiar with inverse trigonometric functions. If you think about algebraic equations, the way we solve any algebraic equations is by using inverse operations. For example, here's a very simple linear equation. We can clearly solve this by subtracting 1 from both sides. But why do we subtract 1? Well, we subtract 1 because it's the inverse of the operation applied to x. Similarly, if I want to solve a very simple linear equation such as this, I'm going to apply the inverse operation of the one that's applied to x. In this case, x is multiplied by the number 2, so I'm going to divide by 2 in order to solve for x. We will apply this same principle to solving trigonometric equations, but we need to be able to use the inverse trigonometric functions. So in section 4.1.1, we'll focus on the first 3 inverse trig functions, the inverse sine, cosine, and tangent functions. Now, inverse trigonometric functions obey all of the properties that you learned about algebraic inverse functions. So let's review that information. Recall that if y equals f of x is a one-to-one function, then all of the following are true. Y equals f of x passes both the vertical and horizontal line tests. It passes the vertical line test because it's a function. It passes the horizontal line test because it's one-to-one. Therefore, number 2, y equals f of x is invertible. So in order for a function to be invertible, it must also pass the horizontal line test. That is, it must be one-to-one. The inverse function, f inverse of x, reverses the operations of f of x. It does exactly the opposite that the original function accomplishes. Recall that if ordered pair AB is a point on the graph of the original function y equals f of x, then ordered pair BA is a point on the graph of y equals f inverse of x. Notice we simply switch the x and y ordered pair in order to generate a point on the inverse function. We could also state this in function notation. That is, if f of a equals b, then f inverse of b equals a. Notice how ordered pair AB is expressed in function notation as f of a equals b, and ordered pair BA is expressed in function notation as f inverse of b equals a. And one last observation, the domain of the original function f of x is the range of f inverse of x, and the range of the original function f of x is the domain of f inverse of x. Where we switched x and y point by point in our example up here, when we switch every single x and y for the entire function, that's also going to reverse the domain and range for your inverse function. Hopefully you had the opportunity to study all of those properties of inverse algebraic functions, and you remember those properties. Keep in mind that inverse trigonometric functions will also obey all of those same conditions. However, we have one small problem. Let's take a look at the graph of y equals sine of x. Recall that for a function to be invertible, it must pass the vertical line test. Clearly, sine of x passes the vertical line test. It's definitely a function. But it must also pass the horizontal line test. That is, I should not be able to construct a horizontal line that intersects in more than one point. And clearly, I can construct a horizontal line on the sine wave that intersects in an infinite number of points. So sine of x does not pass the horizontal line test. This means it is not one-to-one, and it also means it is not invertible. However, you have probably noticed that there is an inverse sine, inverse cosine, and inverse tangent option on your calculator. Look above your sine button. You can see inverse sine is available. So if the original sine wave is not one-to-one and therefore not invertible, how do we explain the inverse sine function? Well, we're simply going to shrink the domain of sine of x down from negative infinity to infinity down to a smaller interval on which sine achieves all of its possible range values, yet the graph is one-to-one. So if you'll notice, this piece of the graph right here, Sine achieves all of its possible values between -1 and 1, but it occurs on a subinterval of the domain. So if we restrict the domain of sine from -π/2 to π/2, then the piece of the graph that we have is 1 to 1 and therefore invertible. Notice this piece passes both the vertical and horizontal line tests. It is therefore a 1 to 1 function and invertible. This is only possible by restricting the domain down to this interval between and including -π/2 and π/2. Also recall from college algebra that a function and its inverse have a special relationship on the graph. If we look at the graph to the right here, we have the graph of the original sine wave, of course, with our restricted domain. That's this piece right here. And we also see the graph of the identity line y equals x. An inverse function reflects the original function across that line y equals x. So when we take our original sine function with its restricted domain and reflect it across that line y equals x, we obtain the graph of the inverse sine function. Notice the domain of this function goes from x equals -1 to x equals 1, and the range is from -π/2 to π/2. We do need to make a small correction here. That should be in brackets. Now, as we stated earlier, the domain of a function f is the same as the range as its inverse function. So you can see how that matches. In addition, the range of the original function matches the domain of the inverse function. So you can see those have switched as well. So the bottom line is that even though the original sine wave is not 1 to 1, we can restrict the domain down to -π/2 to π/2, and we have a branch of that sine wave that is 1 to 1 and therefore invertible. This branch also exhibits all of the possible range values for sine from -1 to 1. Then, when we reflect that graph across the line y equals x, this generates the graph of the inverse sine function. The domain of the inverse sine function is the range of the original sine function, and the range of the inverse sine function is the restricted domain of the original sine function. And that's how we handle the inverse of a function that's not originally 1 to 1. Because the cosine wave is also a sinusoid that is not 1 to 1, we can apply a similar process to cosine to find a piece that is 1 to 1 and invertible and generate the inverse cosine function. So notice here we have the graph of the original cosine wave, the domain of which is -∞ to infinity. It does not pass the horizontal line test, but if we restrict the domain to this branch of the graph right here, then we do have a piece that is 1 to 1. That is, this piece passes both the vertical and horizontal line test. So we're going to restrict the domain from -∞ to infinity down to this subinterval from 0 to infinity. Notice on this interval, cosine will exhibit all of its possible y values in the range between -1 and 1. Then, if we take the graph of this piece of the cosine wave with its restricted domain, and we reflect it across this identity line, we obtain the graph of the inverse cosine function. What's important to recognize here is that the domain of my inverse cosine function is equal to the range of my original cosine function, and the range of the inverse cosine function is equal to the restricted domain of my cosine function. So by restricting the domain of sine and cosine, we're able to get a piece that is 1 to 1 and therefore invertible. We're going to do something similar with tangent as well. If we take a peek of the graph of tangent of x, it does pass the vertical line test. However, it does not pass the horizontal line test. So on its entire domain, it is not one-to-one. However, if we consider this fundamental cycle here in the middle between negative pi over 2 and pi over 2, this piece is one-to-one and therefore invertible. This occurs on the interval from negative pi over 2 to pi over 2. When we reflect the graph of that function across the line y equals x, we obtain the graph of the inverse tangent function. The domain of my inverse tangent function is negative infinity to infinity. Notice that matches the range of our original tangent function, which was also negative infinity to infinity. And the restricted domain of our tangent function from negative pi over 2 to pi over 2, not including those endpoints because there's asymptotes there, that's going to match the range of our inverse tangent function, which would be from negative pi over 2 to pi over 2 in interval notation. Do observe the parentheses on that range. Following that reasoning and logic, and having a good understanding of the parent functions for cosine, sine, and tangent will help you to remember the important details for the domain and specifically the range for our inverse trig functions. So let's state this formally in a definition. For negative 1 less than or equal to x less than or equal to 1, the first three inverse trigonometric functions are defined as follows. Now, this part right here is what we call the domain for inverse sine and inverse cosine. It belongs to these two functions. Because that restriction is upon x, and x is the input to the function, this is a restriction on the argument of the function. That means we can plug in a number between and including negative 1 and 1 into an inverse sine or cosine. The way that we denote inverse sine is with the exponent negative 1, just like we would denote an inverse function from algebra. We are simply recognizing that y equals, we read this inverse sine of x, y equals inverse sine of x provided sine of y equals x. So inverse sine is the opposite or the reverse of our original sine wave. This will yield a value between and including negative pi over 2 and pi over 2. So this is the range of our inverse sine function. This is something to be memorized. It will be important that you know the range of inverse sine. Similarly, inverse cosine has a domain between and including negative 1 to 1. That means I can plug in a number between negative 1 and 1. And inverse cosine is going to generate an output between 0 and pi, another item to be memorized. Now, looking at the graphs that we considered previously, if you remember the graphs, it is a visual support for what we're learning here. Remember, we discussed the range of inverse sine is the restricted domain of sine, and the range of inverse cosine is the restricted domain of cosine. So if I can visualize the basic sine wave and cosine wave, and I can remember where to obtain a piece that is one-to-one and therefore invertible, that can act as a support for helping me remember the range, or just memorize it for pure memory's sake. If I memorize something, I'm sure to forget, so I always want to follow the chain of reasoning of where that information came from and why it is the way it is. Now, inverse tangent is just a little bit different. The domain of inverse tangent is negative infinity to infinity. Now, the reason we know that is because it's the range of the original tangent function. So I can plug anything into an inverse tangent, whereas I can only plug in values between and including negative 1 and 1 for inverse sine and inverse cosine. So it's just a little bit different. And inverse tangent is going to generate a value between, but not including, negative pi over 2 and pi over 2. So again, please be familiar with the range of all of our inverse trig functions. And we're going to practice using this information in a problem here in a minute. Do observe one difference here. Remember, it's always a good idea to compare and contrast as you study, but the range of inverse sine and the range of inverse tangent are really close except for one subtle difference. Inverse sine has inclusive inequalities, so negative pi over 2 and pi over 2 are part of the range, whereas inverse tangent has strict inequalities, so negative pi over 2 and pi over 2 are not specifically part of the range. Now, we said at the beginning that an inverse function reverses the action of the original function, and this is what our inverse trigonometric functions are going to do. So note that the input to an inverse trigonometric function is a ratio. That is, what I'm plugging into the argument is one of the ratios that we've learned from the unit circle. The output is an angle, or you can think of that as an arc. So coming out of those inverse trig functions will have an angle or an arc. It's kind of good to recognize that it's an arc because often our inverse trig functions, such as inverse sine of x, are also equivalently written arc sine of x. So what goes in is a ratio, but what comes out is an arc. Inverse cosine can be written as arc cosine. Notice the double C there. And inverse tangent can also be written as arc tangent of x. So be familiar with both types of notation. This means that when we evaluate an inverse trig function, we're plugging in a ratio from the unit circle, and we're obtaining an arc or an angle, the corresponding angle from the unit circle. So it's still important to know that unit circle. Hopefully you have it memorized very well at this point, and the key is knowing quadrant 1. If you remember quadrant 1 and you can think about reference angles, then that is sufficient to evaluate inverse trig function. Let's try example 1. Evaluate the following inverse trigonometric functions exactly in radians. We'll start with arc sine of negative square root of 3 over 2. So I'm looking for the arc or the angle whose ratio is negative square root of 3 over 2. Now, we know that if we're working on the unit circle and we're dealing with sine, then we're actually looking for the y-coordinate. So I need to find an angle on the unit circle with a y-coordinate of negative square root of 3 over 2. Hopefully you'll recognize two of those. One of those is at, how about 5 pi over 3, right? That has a y value of negative square root of 3 over 2. And also 4 pi over 3 has a y value of negative square root of 3 over 2. However, neither of those locations is the correct answer. Why in the world are neither of those locations the correct answer? Well, it has to do with the range of arc sine. Recall we had to restrict the domain of sine, so we got a piece that was 1-to-1 and invertible. So the range of arc sine corresponds to that restricted domain. We learned that the range of arc sine is from negative pi over 2 to pi over 2. This means I need an angle from negative pi over 2 to pi over 2 on my unit circle. So from negative pi over 2 to pi over 2. So I'm looking for an angle either in quadrant 1 or quadrant 4. So that's immediately going to rule out 4 pi over 3. But why does it also rule out 5 pi over 3? Well, 5 pi over 3 starts at the positive x-axis and rotates in this direction to its terminal side. Notice it goes beyond pi over 2. So 5 pi over 3 is outside of this interval right here. 5 pi over 3 is bigger than pi over 2. Perhaps it would be easier to think about it in degrees. If we were to write the range in degrees, we would say from negative 90 degrees to positive 90 degrees. Well, if we rotate to the terminal side of 5 pi over 3, we know that's 300 degrees. Notice 300 degrees is outside that interval there. But do not fear, we can fix this very easily by rotating in the negative direction. Notice this angle would be negative 60 degrees, or in radians, that would be negative pi over 3. Just like negative 60 degrees is in the interval between negative and 90, negative pi over 3 fits in this interval. Therefore, we can conclude that arc sine of negative square root of 3 over 2 is negative pi over 3. So that's definitely a lot to think about. Now, you can support this work with your calculator. I notice up at the top of my calculator, it displays the fact that I'm in radian mode. So when I evaluate inverse sine, remember inverse sine and arc sine are the same thing. When I evaluate inverse sine of negative square root of 3 divided by 2, it's going to give me the result in radians. Well, I can certainly compare that to my answer, negative pi over 3. Compare the decimals and see, yes, we have evaluated it correctly. Or you can certainly convert all that information over into degrees. So I'm going to switch to degree mode. I'm going to retype inverse sine of negative square root of 3 over 2. I can see negative 60 degrees. That's equivalent to negative pi over 3. So it's really important to know the range of each of these inverse trig functions in order to correctly identify which angle is going to be our answer. Let's try that again using our friend, the unit circle. So our next question here is inverse cosine of negative square root of 2 over 2. Remember, what's going into the inverse trig function is a ratio, or either the x-coordinate or the y-coordinate, depending on your function. In this case, it is an x-coordinate. So this is an x-coordinate from the unit circle. Coming out is going to be an angle or an arc. So I need to find an angle on the unit circle whose x-coordinate is negative square root of 2 over 2. And we've got two candidates. We've got 3 pi over 4 and we have 5 pi over 4. Both of those locations have a cosine value or an x value of negative square root of 2 over 2. However, I only want the one that falls in the range of inverse cosine. Recall that we took the original cosine wave and we restricted the domain down to 0 to pi because that piece was 1 to 1. So the range of cosine, inverse cosine is 0 to pi. So I'm looking for an angle between 0 and pi. This time it looks like the easy and clear winner is 5 pi over 6. And we could certainly verify that with our calculator. Since I'm already in degree mode, I'm going to keep it in degree mode. The answer will come out a little nicer that way anyway. I'm going to type in inverse cosine of negative square root of 2 divided by 2. It's going to spit out 135 degrees, and we know 135 degrees is equivalent to 5 pi over 6 radians. Let's try arctangent of square root of 3 over 3. Remember, what's going into the arctangent function is a ratio from the unit circle. In particular, tangent is obtained by finding the ratio of y divided by x. So I need an angle on the unit circle that when I divide the y-coordinate by the x-coordinate, I get square root of 3 over 3. Now, as your familiarity with the unit circle has grown, you can probably figure out this is going to occur when the y-coordinate is 1/2 and the x-coordinate is square root of 3 over 2. In this case, the denominators cancel, and we end up with 1 over square root of 3, which when we rationalize by multiplying by square root of 3 over square root of 3, we end up with square root of 3 over 3. So I'm looking for an angle on the unit circle whose y-coordinate is 1/2 and whose x-coordinate is square root of 3 over 2. So on our unit circle, we can identify that to be pi over 6. There is, however, one more candidate on the unit circle whose tangent value is square root of 3 over 3. You know what I'm thinking here? 7 pi over 6, right? Negative 1/2 divided by negative square root of 3 over 2 would also give me square root of 3 over 3. So we have two candidates, but only one answer. Recall that the range of arctangent is equal to the restricted domain of the original tangent function. Think about the graph of your original tangent function. That first fundamental cycle is between negative pi over 2 and pi over 2. And because we had asymptotes there, we need to use parentheses. So I'm looking for an angle between negative pi over 2 and pi over 2 and not beyond those boundaries. So the only correct answer here would be our first choice, pi over 6. And of course, you could certainly check that with your calculator. Now, to finish off, we are going to look at a few that don't come out quite as nicely. These don't yield unit circle angles. On example 2, we're going to find alpha to the nearest tenth of a degree. So this gives me permission to round. So sine of some angle alpha equals 0.557, which means alpha is going to be inverse sine of 0.557. So I'm just applying the inverse sine to both sides, and then we can type this into our calculator. I am already in degree mode, so I can evaluate inverse sine of 0.557, and we'll approximate to the nearest tenth of a degree. This gives us about 33.8. Now, the good thing about your calculator is it is programmed with the correct range for all of our inverse trig functions. So when you evaluate an inverse trig function with your calculator, you're sure to get a value that falls within the appropriate range. Let's try the next one. If cosine of alpha equals -1/5, then the angle alpha is equal to inverse cosine of -1/5. So we'll just type that into our calculator. Second cosine accesses our inverse cosine. The ratio is -1/5, not a familiar unit circle value. This gives us a value of 101.5 degrees. Now remember, 101.5 is between 0 degrees and 180 degrees. It's in the appropriate range. For our last one here, tangent of alpha equals -57. So alpha equals inverse tangent of -57. Now, whereas the input to either inverse cosine or inverse sine has to be a value between -1 and 1. Remember, we can plug anything into the inverse tangent function, anything between -infinity and infinity. So we'll evaluate inverse tangent of -57. And we obtain -88 we're going to round this to the nearest tenth, so we better call that -89.0. So approximately, squiggly equals means approximately -89.0. Notice that's a value between -90 degrees and +90 degrees. Now, very quickly, let me show you what happens if I tried that with an inverse sine. If I did inverse sine of -57, the calculator is going to tell me it is a domain error. Once again, what we plug into an inverse sine or an inverse cosine has to be between -1 and 1, but we can plug anything into an inverse tangent function. So this is a lot of detail. Take some time to absorb the detail, and remember, it's vitally important that you know the range of inverse sine, inverse cosine, and inverse tangent.